type of gas stack, two different insulating silicon oxide layer, and two different gate electrode, titanium nitride and the polysilicon. We measure the IV curve at different temperature from 300K down to 4K, and we extract their mobility at different temperature. And we put 300K mobility here. They are here, 300K mobility here. And we use the same device to measure the noise, to analyze the noise, the flicker noise, and then we extract from the noise spectrum, we extract the oxide trap density along the oxide thickness, and we put the average. It's very flat along the. Seems very uniform. So we put the oxide trap density here. But we still measure all these results at room temperature. So in this plot, we establish a electrical correlation between MOSFET mobility and the oxide trap density. They are all extracted at 300K. As you can see, if you want a higher mobility, you must reduce and optimize your process and to reduce your trap density. Okay, we use the same four gate stack, and we measure the whole bar mobility at 10 milli-K. So we extract the mass whole mobility and the critical density at 10 milli-K, and we put here. So again, this is the room temperature parameter, and this is the device parameter at 10 milli-K. As you can see, you can again establish the correlation between this device parameter. So the spirit of this work is that if you have this correlation, you don't need to characterize your fabricated device every time at very low temperature. You just need to compare their room temperature characteristics, and you can tell which one gonna perform better at lower temperature. So in this sense, you can speed up your device optimization and the process fabrication. And this work, we also identify oxide trap is the limiting factor for the gas stack quality. Okay, for cryo CMOS, if we want our system work faster, we always want our on-current as high as possible. So compared to silicon, germanium has a higher hole mobility and electron mobility because their effective mass is lower. So we demonstrate germanium transistor and measure them at low temperature down to 10K. So by this work, we prove that germanium cryogenic CMOS is promising for high-performance computing. So for high-performance computing, if we want to have more functionality on a single chip, we want to have our device areal density as high as possible. To do that, instead of shrinking your device dimension, we can also stake our device vertically. So to do that, non-crystalline channel transistor is one of the possibility. So we fabricate silicon thin film transistor and characterize them at low temperature. That's the result from 300K down to 100K. And we extract the device parameter. Here I show you the band tail against the temperature. You see it's decreasing because of the reduced thermal fluctuation. And the mobility is decreasing. That's because with non-crystalline channel, the carrier transport mechanism is dominated by hopping. So for carrier to hop, you need provide them enough semionic energy to jump out, to jump from trap to trap semiotically. So that's why you see the mobility is decreasing with temperature. Interface trap density is also increasing with temperature. That's probably because you have two different material at the interface. Non-crystalline silicon channel and the amorphous silicon oxide. They have different thermal expansion coefficient. So when you reduce the change the temperature, you change the strength at the interface. This is probably the reason why you see a different DIT interface state at different temperature. So as I mentioned, for high performance computing, we want to reduce the power consumption of the chip as low as possible. To do that, we can reduce the temperature and reduce the supply voltage. We need to reduce these two parameters at the same time. But how to do that? We tried 5 different strategies. The first one is we start at 300K with 0.9 supply voltage, and we scale the supply voltage with temperature linearly this way. And the other 4, we saturate the minima VDD at a certain value. With this 5 scaling strategy, we measure TSMC 14 nanometer technology node test key. We obtain their IV curve. We extract their performance against the temperature for 5 different strategies. And we translate the data in the previous slide into total power. Here, the total power means chip power, not cooling, without including cooling power, of course. And also the operation frequency. Here, we took the reference at 300K. So this is the quarter. This is the corner we want to reach because we can have a lower power but higher frequency. So if you reduce scale VDD down linearly, you can only save your power, but you significantly sacrifice your operation speed because you don't have sufficient bias to increase the current. So if you saturate your minimum VDD, and eventually you can have saved power, but higher performance compared to that at 300K. Okay, this is my summary. So the requirement for classical controller, it must be scalable, low power, show functionality at low temperature, and it must be able to integrate with qubit. So Cryo-CMOS is one of the best candidates. If you reduce temperature when you are operating MOSFET, you see a lower of current beta swing, steeper subfacial slope, and a higher on current. On top of Bentel, source to drain direct tunneling is another reason of subfacial swing. And this also, this factor also may pose challenges when you are trying to scale up the Cryo-CMOS together with qubit. Correlation of electrical property of MOS device at 300K and mini-K has been is demonstrated. So we optimize our device like that. And the best optimum VDD for TSMC N40 MOSFET is about 0.5 volt, but the device must be operate below 100K. The challenge for thin film transistor working at low temperature is that they show degrade swing, lower current, and increase the threshold voltage. Thank you very much.
Thank you for your very interesting talk. Do we have any questions?
Frank, thanks very much for the interesting talk. I have 2 questions. So the first not so serious question is, how do you estimate the number of cables that you need when you go to 1,000 qubits?
The cable for
The number of cables, you say
Yeah.
maybe of the order of 3,000 or something like that. How do you estimate that?
Wait, let me go back to the slide.
Maybe